So welcome to a course on conduction heat transfer. So we will be going through all the basics of heat transfer principles from my point of view. So basically I'm an engineering student. So let's go through the basics. So when you think about conduction heat transfer, so conduction heat transfer is basically the heat transfer that happens due to the vibration of particles. So consider a small slab, So due to the particle vibration, the heat transfer happens along the slab. So once the heat transfer happens, for the heat transfer to happen, there has to be a temperature difference. So T1, T2. So we can define this heat transfer by using the Fourier's law. So Fourier's law states that Q dot X is equal to negative thermal conductivity into cross-sectional area into dt by dx. So dt by dx is the temperature gradient. So that is basically, let's think here, if you have T1 0, here you have T1 2, and you have a distance dx. This gradient of temperature among these 2 points is called dt by dx, or the temperature gradient across this. So due to the temperature gradient, it is what drives the heat transfer. So if I highlight about area, so if you consider a simple bar or a simple rod, the area would be the heat transfer that happens across this circular heat transfer. So the heat transfer happens perpendicular to the cross section. So this is defined as the cross-sectional area. Area AA. So I would like to dive a bit more interestingly. Let's think about the heat, how temperature changes along the bar. So let's consider a bar of length L. So this is temperature, this is X. So simply the heat transfer happens like this. So the temperature gradient is represented by this. So now if I draw it further nicely, Q dot, and then this is the cross-sectional area, bar or the beam or the wall of cross-sectional area A. Now a few more interesting things which you as engineering students need to understand. Heat transfer can actually happen in Z direction, X direction and Y direction. So respectively, we can have Q dot X, Q dot Z, Q dot X and also Q dot Y. But in our engineering applications, we assume the heat transfer to only happen in one direction. So in most cases, we assume that heat transfer only happens in the axial direction. Q dot X is much greater than Q dot Y and Q dot Z. That is one main assumption. The second assumption that you understand is that the thermal conductivity, we assume the Kx, Ky, Kz. So in all X, Y and Z directions, we assume thermal conductivity to be the same. So that is, we assume it's an isotropic material. The next assumption which we use is that steady state heat flow. What does steady state heat flow mean? So steady state heat flow means that the variation of temperature with time, or the variation of heat flux with time, is zero. There is no time dependence. Now let's go for application. Time for application. So on my simple heat transfer course, I will first start off the application with a plain wall and plain slab. So assume the plain wall or plain slab to be of thickness L. To assume the plain wall to be of thickness L. So for this plain wall of simple L thickness, the Q dot is equal to what? It's K times A times temperature. If you assume here T1, if we assume here T2 is into T1 minus T2 divided by L. So what is this? The temperature gradient, dt by dx. Simply. Now we will think about the electrical principle. We are going to combine the idea of thermal heat transfer with electricity. Ohm's law, interesting thing. So when we combine it, let's draw a circuit to represent the wall. Let's have the temperatures to be T1 and let's have it to another one temperature at the end of the wall to be T2 respectively. And we'll have the heat flux to be Q dot O. So we can write it as Q dot O is, we can rearrange this equation to write an T1 minus T2 divided by the length divided by thermal conductivity times cross-sectional area. So if we use the principle of voltage is equal to current into resistance, we can write the voltage to be the driver. So what is the driver here? Temperature, T1 minus T2. What is the current? Q dot 0, the heat flux. What is the resistance? That's what comes here. It is L by K A. So this is what you call the thermal resistance. Thermal resistance, new thing guys, interesting fact. Now let's dive into a nice plain wall, a composite wall, a nice example. Let's dive into a nice example of a plain composite wall. So guys, last thing we have one wall of thickness L1, another wall of thickness L2, a sandwich panel I would say, L3, another thickness. So we have 3 thicknesses. We have the heat flux Q dot O entering there. We have the temperatures T1, T2, T3, T4. So in terms of the circuit principles, we can write this as, so we could write this as T1, T2, R1, T2 to T3 as R3, thermal resistance 3, thermal resistance 2, sorry. And then here finally, T3 to T4, you can write it as R3. So we have 3 resistors. So what is this? Series type heat flow. Series type heat flow. So if in this simple circuit, you can understand simply as current is in a series goes through all, the heat flux also goes through all. The heat flux also has to go through all. So then what happens? As engineering students, I would assume you would know that the resistance answer. So R equivalent is R1 plus R2 plus R3. So we can represent the Q dot O as T1 minus T4 divided by Req. Nice. That's the first example for you guys. So forget one thing I want to tell. This is K1, K2, K3. So composite walls will have different thermal conductivities because that's very important to note, right? It's a practical application. Okay. So that was basically introduction to conduction, heat transfer or Fourier's law, and how we combine heat transfer principle into electrical principles, or the V equals IR principle notion of heat transfer. Next, in the next video, we'll be diving bit more detail into walls. So we will be looking at series and parallel heat transfer, series and parallel heat transfer in composite walls, and also we will be looking at interestingly heating tapes in walls and what happens in that scenario and how we solve those problems. Cheers, and let's have a nice course.